here, this is my talk, and so batch online learning and decision making. So online learning and decision making, so is just as mentioned, like in the morning by a few panelists. So it's a relative new paradigm compared to other machine learning paradigms, such as supervised learning or unsupervised learning. So here, the difference is that the learner can interact with the environment and actively collect data to figure out to learn the optimal solution of some optimization problems in a more efficient way. And recent years, it has been proven to be quite successful in many practical applications. So one simple example is the so-called multi-arm bandit problem. So as many of you may already know that. So here, in this problem, so we have quite a few arms. So here we have k arms. Usually we can also refer to them as, let's say, actions. So each time when the player plays an arm, then he would observe a stochastic reward, and the expected reward would be so an intrinsic value associated to that arm. Of course, this value, this expectation is hidden from the player. And the player's goal is just try to learn, to use exploration, to use interaction with these arms to figure out which arm would produce the best reward on expectation, okay? So he would play it for like a sequential of t rounds, and the goal is to maximize the total amount of rewards. And so equivalently, this is also the same as, say, to minimize this notion of regret. So that's just the difference between, so I star would be the best arm, so the difference between the reward of the best arm and the arms played by the player. And of course, so this is the simplest version of the, let's say, online learning problems to characterize this famous dilemma between exploration and exploitation. That is, so on one hand, the player would like to play as diversely as possible to figure out which arm, to learn the arm's expected reward, right? On the other hand, he would have to concentrate on the best arm in order to collect the rewards. And it has been proven to be useful in many applications, such as online advertisements, recommendation systems, and let's say here a clinical trial. So indeed, let's say for a clinical trial, so all these actions would correspond to a possible different kind of treatments, right? And the reward would just be whether the treatment is successful or not. So this is multi-arm bandits. So another version is called the linear contextual bandit. So this is just a more generalized version of multi-arm bandits where we can introduce features to characterize the, let's say, personalized treatments. So let's say, so in this model, so we have, for each arm, so we have some personalized feature vector. And so this can be viewed as, let's say, again, using the example of, let's say, a clinical trial. So this would correspond to the feature extraction of, so the pair of patient and the treatment. And now the reward becomes a linear function of this feature vector, so defined by the theta. And the theta vector is hidden from the player, and the player's goal is just to figure out, to learn this linear function from the observed rewards. And also this reward is kind of is stochastic, so we have a noise here, so epsilon would be a centered noise. And okay, so this is a paradigm, okay, still like say every time we see this, so the player would see a set of arms and correspondingly see the set of the feature vectors. We also call it the context, so it may be drawn from some unknown distribution. And then the player will choose one of the arm and receive this noisy linear reward. And the learner's goal is just try to learn data and minimize the regret. And the final example I want to mention is the, let's say, to learn the Markov decision process, or we just call it, we may also call it reinforcement learning. So this is so even more general. And here the agent would interact with the environment. And so the generalization here is that the environment has state. So here, the environment would be modeled by this Markov decision process, and it has a state space. And again, the agent, the learning agent, would play some action, and then based on the state, and then he would receive this reward also based on the state and the action. And then the environment would, using this transition probability function as a matrix, to go to a new state. So here, instead of like a one-shot decision in the previous Bandits problem, so here the agent would make a sequential, a sequence of decisions and try to maximize the total reward in this sequence. Recently, so this has also been proven to be very useful in many areas. Again, I will use medical treatment as example. So as we can see that, so in many like more complex diseases, the treatment may involve like many stages. So it involves a sequential interaction between the doctors and the patients. Indeed, so here I just quote like one of the very recent paper here. And the researchers have been using the Markov decision process to model the treatment process of diabetes. And the state here is just like a vector of all these like sub variables. Let's say whether the patient presents like a chronic or acute symptom, and also some other things like the fasting plasma glucose level and so on. Okay, just give you an example. And so all these are the successful examples of online learning and decision-making problems. And however, so in all these problems, so what the player needs to do is to make sequential decisions. So by this sequential decision, the player would be like benefit from the being adaptive to all the data he collected before the current time step. However, it also has many problems. Say, first, so the most significant problem is the learning process is very slow. So take the example of clinical trial, for example. So the treatment of each patient may involve like many days or even months. So then we do not have this chance to go through one patient after another. So it would take like a very long time, right? So this also would result to very poor scalability because we cannot treat like many patients in a very short time if we want to do it like in a sequential way. And to solve this problem, indeed, so people already have this figured out this way, as you can see that all the clinical trials would run in batches, or say in stages. So this would introduce our notion of batch learning. So this just perfectly corresponds to all the phases of the clinical trial, right? And this is also one of my recent research focus on reinforcement learning, also online learning. So more concretely, so this batch learning model, so here we have all these time steps. So originally, so each time step would correspond to like a patient or some data point. So then they are grouped in predefined batches. Say the first batch would consist of like T1 patients or data points, and then the second one would consist of T2 minus T1 data point, and so on and so forth. And within each batch, we would only apply the same policy to select actions for all the data in this batch. And then all these rewards are only observed at the end of the batch. So for example here, so let's say at the second batch, so the player would decide his policy pi k at the very beginning of the batch and apply this pi k equals to 2 to each data point. So here you can do it like in a simultaneous way, in a parallel way, in order to make things to go fast. And then at the end, the learning agent will collect responses and start a new batch. So in the third batch, so all these responses would be provide information for him to decide the policy for the third batch. So this policy pi k, let's say for example in multi-arm bandits, so it can take the only parameter it can take is this time t, and it would return an arm or a distribution of the arms. Very easy, right? And for linear bandits, so it can take the input as t and also the current context, xt. And again, it would output a distribution over the arms. And for reinforcement learning, it's a little bit more complex. It's similar, right? So we have the time step t and the current state s. And then the return would be, so it would output a distribution of the actions. So this is the batch learning model. And So our focus on this batch online learning problem, so the most important question, of course, is what is the minimum number of batches we need to achieve the optimal performance? And here, the optimal performance we mean is just when we do not have the batch constraint, or say when we do things in a fully adaptive and sequential way. So can we use like smaller number of batches and smaller amount of adaptivity to achieve the same amount of regret? And so these are some recent developments. And so in 2009, so Gao et al., so they studied this problem studied this question on multi-arm bandits, and they say that only log T batches are needed. So this is quite a encouraging news, right? Because log T is quite small. And for linear bandits, so people like Han et al., so they studied this problem and also gave a affirmative answer for log T. However, they propose so their solution needs some additional assumptions, which are we are not sure like how to, first they are kind of restrictive, and the other thing is that we are not sure how to directly remove them using their framework. And so then I would like to introduce our work on linear bandits. So this will be on the full framework of linear bandits without assumptions. Then we say that for this general linear bandits problem, so only log T batches are needed. And this is indeed optimal to achieve the optimal performance without the batch constraint. Okay, so this is one of our results, recent results. And I guess I only have a few minutes, so I will briefly introduce our key techniques here. And the key technical challenge here in batch linear bandits is, indeed, you see that we do not have the full adaptivity, and we need to plan ahead, especially to plan the exploration in the batch. And to do this, so we find a connection to the classical statistics, so-called the optimal experiment design, and we will develop a useful extension from them. Okay, so more specifically, so let's first briefly introduce the classical G-optimal design. So here we have a set of candidate data points X, and we assume this noisy linear model. And we say that to design the experiment, so we will choose some data points and to receive the corresponding linear response. And to design this experiment, so we need to come up with a distribution pi over X, and you imagine that each time we want to figure out which data point we want to do the experiment, we just sample a data point from this distribution. And to measure the efficientness, so we define this G variation of this distribution. So it's just in this way. You see that, so in this maximization, so here this is so-called the information matrix, and if we do the linear regression, so here, so inside the max here will just be the estimation variance at X per experiment from pi, and we want to figure out, so here the measure is just, we care about the maximum possible variance at a data point. And we want this maximum variance to be as small as possible. And the classical result says that for any set of data points, so there exists such a distribution such that this G variation is bounded by D, and indeed this is optimal. And for our batch linear bandits application here, so indeed here we would generalize this to a so-called distributional optimal design. And indeed here, so the difference here is that this set of candidate data points X becomes stochastic. It is sampled from a unknown distribution here, and again we assume linear model. And now if we design, our design of experiment becomes a distribution pi X over X, because this X is not predefined, it's stochastic. And the distributional G variation becomes in this form. So you see that the only thing different here is that we add the expectation here. And so in here we have so U is sampled from, so this experiment is sampled from pi X. Okay? And indeed, the connection to the linear bandits is that this D will correspond to the context distribution. And so you see here will just be the largest estimation variance of any arm. So we treat each X as an arm in the context set. And we want to minimize the expected largest estimation variance. And our goal is trying to generalize the classical theorem as we would to say that for any distribution of context, can we figure out a policy pi such that this distributional G variation is small? And our answer is affirmative, and it can still be roughly D, and indeed this pi can be learned from a few samples from D. So this is important because not only we need to care about application, care about computation, we also care about the learning efficiency. And indeed, so we come up with a parametric form of this distributional G-optimal design, because you see that previously, so this kind of thing is kind of, it has like infinite dimension, and so this pi could have infinite dimension and it's hard to learn. So we come up with a parametric form, so due to time limits, so I have to skip this form. But indeed, what we can prove is that this parametric form has only a finite number of parameters here. So n is at most d log d. And using this parametric form, so the distributional G variance can be bounded by order of d log d. And not only we prove the existence of such a good parametric distributional G-optimal design, we also show that there is a sample efficient algorithm to learn such a policy. And indeed, I want to mention that, so this theorem is significantly different from the previous theorem because simply using the sample average approximation may not work. So we need to come up with a new learning algorithm. And this is also the crucial component of this log T batch learning algorithm for linear bandits. And very quickly, a few recent developments. So recently, we also come up with, so with Zhang et al., we also come up with a full range and tight batch regret trade-off for linear bandits. And this is our theorem. You see that, so this regret is, so for any batch number m, so this is the regret, and we also prove it is optimal. And you see that it's very curious because this seems to be complicated and not very natural, but it turns out to be indeed optimal for all the parameters. And the key technical ingredient is that we need to prove a new matrix concentration inequality with dynamic upper bounds like this. And so I would say that, so using the usual Chernoff bounds, so we may prove this for some constant upper bound. But so there are also some, let's say, Friedmann's inequality due with the dynamic variances of these matrices. But here, what's different here is that our upper bounds of per stochastic matrix can be dynamic. And this is the first time in the literature to do that. And to prove this involves some very kind of a very interesting matrix analysis about Lieb's theorem on convex trace functions, which I do not have time to go through. And another recent, our ongoing work is for batch reinforcement learning. And here the key challenge is, again, try to design and learn and design this planned exploration for Markov decision processes. And that ends my talk. Thank you.